Now, officially today, we're going to get mathy again. In Unit 4, we're going to be doing problems like this. Combustion of methane, CH4, to carbon dioxide and water. How much water is produced if 15 grams of methane are consumed? That's a Unit 4 question. But we've got to build to that. And there are two main parts to that question. One is the chemical reaction, which we're going to talk about tomorrow, and also the concept of the mole. And the word mole comes from the word molecule. Okay, so all areas of science, engineering, health have convenient units. For example, pH, convenient unit to measure the strength of an acid or base. When you take when you check your blood for glucose levels, it's in a very strange unit. And everyone goes, what's your glucose level? And everyone goes, oh, it's 100, if you're diabetic, it's like 180 if you're fasting. But no one knows what that is. And if you look at the actual units, it's very strange units. But what they do is they modify units so that working with them is convenient. Like if you're an egg farmer, what's the most convenient unit for being an egg farmer? Dozen. It's just totally random. And a dozen doesn't necessarily apply to eggs only. You can have a dozen chickens, you can have a dozen students, a dozen lambs. It's just a number, but it's convenient. If I was a paper salesman, what would be the unit I would typically use? Exactly, a ream. A ream of paper, usually used to buy copy paper by the ream, which is about that much paper. Now they sell it for the same price, but you only get 400 sheets rather than 500 sheets. It's the clever way of marketing to disguise the price going up. But it's convenient. It's 500. Doesn't matter if it's pieces of paper or chickens. It's the number. Well, if you look at this, the less something weighs, the bigger the unit we use. So if something is really, really, really small, like atoms or molecules, the unit we're going to be using is going to be really big. Again, for convenience only. Look how big that number is when we're dealing with atoms and molecules. And when you get into physics, it'll be electrons. 602 times 10 to the 23rd. That's a big freaking number. That's 6 with 23 zeros after it. 23 zeros. That tells you how small atoms and molecules are. But again, it's just a number. Now, that's not a, by definition, number. The real number has probably 30 or 40 decimal places. So 6.02 times 10 to the 23rd is going to have 3 sig figs. And we call it a mole. And that word, again, comes from the molecule. Okay. Now, we're going to be doing conversion factors for Unit 3, the second half of Unit 3. So this is going to be your first conversion factor. And I'm going to put atoms here. But it could apply to molecules as well, or chickens, or students. It's just a number, just like it doesn't. It doesn't specifically apply to any discipline other than it's convenient in chemistry and physics. Convenience. Okay, and like all conversion factors, we have the inverse. Okay, and this is for anything. Any chemical. Okay, if we look on the periodic table, and I need to have a periodic table. Let me grab a periodic table here. I've got periodic tables all over the place. Why can't I find them? Okay, that didn't take too long. Okay. Now we learned in Unit 2 that a periodic table for each element, it's got two numbers. An integer, which is the atomic number and also refers to the number of protons, and also a decimal number. Now, that decimal number is called the atomic mass. What that is so if we took a mole of carbon atoms and weighed it, it would weigh it would weigh 12.01 grams. Now, if it's a molecule we're talking about, like water, then it would be a molar mass rather than atomic mass. So atomic means there's just one element there. Molar means it's two or more. But that's what the decimal number means. So for example, if we had water, we would take so the molar mass for water would be, well, each hydrogen is 101. Two of them would be 202. Plus 16 would be 1802 grams per mole. Or the inverse of that. So that's our second conversion factor, is the atomic mass or molar mass. Now that's specific, very specific to the compound we're working with. It's not general at all. It only, and I want to emphasize this, it only applies to the specific compound. 18.02 is only valid for water, no exceptions. Unless we're talking about a specific isotope of water, like heavy water. During World War II, the Manhattan Project used heavy water reactors. So that water, molar mass for that water is for a specific isotope. So it wouldn't be 1802, it would be something else. But if we're just talking about generic water, go to the tap or go to our deionized water tap, pull out X amount of water, which is pretty pure water, not perfect, but pretty pure. We're going to get 18.02 grams, which is a mixture of many isotopes, not just one. Okay, so that's the second conversion factor. So we have 6.02 times 10 to the 23rd applies to anything. The molar mass only applies to the compound that is specified. And then there's one more, and that's when we're working with a gas. Now, gases are very different than liquids and solids. Why do you think they would be different? I'm sorry, what? Right, but why would they be so different than a liquid and a solid? I mean, you're absolutely right, but why? Yeah, exactly. The molecules are very far apart. Now, liquid, the molecules are kind of kissing each other, and with a solid. Gases are the opposite. So because they're so far apart, you can compress a gas. Liquids are very difficult to compress as well as solids because they're so close together already. Gases, you can expand them, you can compress them, all kinds of stuff. So when we're working with a gas, so for a gas only, 22.4 liters per mole, or 1 mole is 22.4 liters. That's the other conversion factor. Now we're going to be using these three conversion factors a lot from now to the end of the semester, a lot. So you get very used to using them. But this only applies to gases, though. No exceptions. Now, because gases can compress and expand, we have to specify two things whenever we talk about gases: temperature and pressure. At standard temperature, 0 degrees centigrade, 1 atmosphere, that gas will occupy 22.4 liters. No other specifications. If we go to 100 degrees centigrade, the gas is going to be much bigger than 22. Well, if we go below 0, it's going to be much smaller. But at standard temperature and pressure, STP, it's 22.4 exactly. Okay, so those are the three conversion factors you're going to be using a lot. A lot. Particularly number 2. And I'm talking about the rest of the semester. Okay, so let's look at some problems. Just as a harbinger of today's lab, we're taking copper sulfate, really pretty blue copper sulfate, solid, and we're going to heat it. What's going to happen is the pretty blue solid has got water around it. And that's the definition of a hydrate, where the water actually binds to the copper metal. However, if you heat it, you can drive off the water. So to determine how many waters stick to the copper or bind to the copper, we heat it. We heat the dickens out of it. We drive off the water. Then we weigh it again. The difference in the weight or the mass is going to be how much water comes off. And then the goal in this lab is to find out how many moles of water comes off. If a chemical has got water attached to it, it's called a hydrate. If it has no water but used to have water, it's called the anhydrate. And it goes from this really deep blue to this, only a mother could love, powdered, light blue, unattractive copper sulfate. Okay. Let's look at some problems now. Okay, how many moles are in 2.34 grams of water? And we just calculated the molar mass for water. It's 18.02 grams per mole. So given, now this goes back to unit 1. What's given? .34 grams of water. And what are we trying to calculate? Moles of water. Do we have a conversion factor with grams and moles in it for water? We just calculated that. We want the grams to cancel, so grams need to be in the bottom. And we end up with moles. Okay, we've got 3 sig figs, 4 sig figs. Our answer is going to be 3 sig figs. By the way, the molar mass on the periodic table, none of them are by definition unless it's in parentheses. Everything else is an estimate. So go by sig figs out of the periodic table you're using. God, I can't run. So 0.130 moles of water. Now this is about as simple as you can get problem. Now we're getting into something called stoichiometry. Stoichiometry is a fancy word Okay, so stoichiometry is an analytical relationship between reactants and products of a chemical reaction. So this is the front end of that, the very front end of that. And stoichiometry is the total focus of Unit 4. That's all you'll be doing in there, just stoichiometry. But you're going to be using these relationships big time. Number of particles, atoms and molecules in a mole, the number of grams per mole, the number of liters per mole as the front end to stoichiometry. Okay, and then the kind of the opposite reaction, the problem we just did. How many grams are in 12.45 moles of water? Okay, so 1245 moles is given. And we're trying to calculate grams. So we're going to use the same relationship between moles and grams as the previous problem. Only this time the given has to cancel. So that means moles are on the bottom. So 4 sig figs in the answer. Now this is very, very, very similar to our Unit 1 problems, only we're doing chemistry now. Okay, are there any questions so far regarding these calculations? Yeah. You need to know those three, but you're going to be doing so many problems, you'll kind of know them automatically. Well, the easy one is the periodic table. So that one, so yeah, I'll be giving you a periodic table. But the other two you need to know, the 602 and the 22.4. Okay, so let's do a little different one now. Let's do okay, how many liters of H2O gas is in 2.34 grams of water? Okay, so the given is 2.33 or 34 grams, and that's water. Notice I'm putting the chemical above it, because when we get into full-blown stoichiometry, not only do the units need to cancel, the chemicals need to cancel as well. So get used to putting the chemical we're working with along with the unit. Okay, so 2.34 grams of water, and we want to go to liters. That's gaseous liters. Now notice we haven't changed chemicals. All we're doing is changing the units of that, but there's no chemical reaction. A chemical reaction, you start with something, you end with something different. Then there's another step involved if that's the case. But we're not doing that. We're keeping with the same thing. We start with water, we end with water. We start with copper sulfate, we end with copper sulfate. No chemical reactions yet. By the way, what we've done so far in units 1 and 2 and half of unit 3 is covered in 1 week in 1A. That's why this class is really important, because they're assuming that it's review for you. So they zoom through it. Okay, so how are we going to do this? Is there a conversion factor with grams and liters in it? No. So I'm going to give you a truism you're going to use for the rest of the semester. If in doubt, convert to moles. If in doubt, convert to moles. Then from moles, you can go everywhere. And that's almost a true statement. There's a few things you can't go to moles. It requires another step or two. But in general, if you're in moles, you can go so many places. So let's go from grams to moles. First thing. And let's do train tracks this time. Okay, so we know how many grams are in 1 mole of water. Now we've got moles of water. Let's go to liters of water at STP. Okay, that's going to be moles on the bottom, liters on the top. So now via moles, we've gone from grams to liters. And we're looking at 3 sig figs. So the 2.34 grams converts at STP 2.91 liters of gaseous water. Now, water is not a gas at 0 degrees centigrade. It's actually a solid, but the only way we can convert gaseous is with standard temperature and conditions. So we're going to play like water is a gas at 0 degrees. Okay, does this problem make sense? This is real reminiscent of Unit 1 stuff. Okay, how many molecules of water are in 3.45 liters at STP of water? So given is 345 liters. And do we have anything that goes from number of molecules to liters in our conversion factors? No. So if in doubt, we convert to moles. Oops. And now we've got moles of water at STP. Now we're going to convert over to molecules of water. How many? Okay. Keep that in your mind. Whenever you have to do how many of something, think of the 602 times 10 to the 23rd. By the way, that is officially given a name. Avogadro discovered that. So that number is Avogadro's number. If you ever go to Trader Joe's, they used to advertise guacamole in terms of Avogadro's number. They were very clever. At least in Tacoma, they did. All the Trader Joe's are a little different, but they were really clever using that. Anyway, so another name for 602 times 10 to the 23rd is Avogadro's number. Let's see, where did I leave off here? Okay, so now we have moles. So let's go to Avogadro's number. Now this can be molecules or atoms. Depends on what we're dealing with. Now, water is a molecule. It's not single. So then we're going to be using the molar mass. Excuse me, we're going to be using the 602 times 10 to the 23rd molecules rather than atoms. Okay, so moles cancel, gives us number of atoms, excuse me, molecules. Okay, and we're looking at 3 sig figs all the way across. Now, a lot of people ask me, is there abbreviation for molecules? There is. Unfortunately, it's MOLC. The problem with that abbreviation is if you're sloppy making your C's, it looks like an E. So I usually don't use it, but there is abbreviation. So if you're real careful when you're putting these numbers out and letters out, you can use MOLC. Okay, so 3 sig figs all the way across. We've got 9.27 times 10 to the 22nd molecules of, starting with water, ending with water. Okay, let's do another flavor of this. How many atoms of hydrogen are in 3.45 liters of water? Now, I want to be very specific on this problem. I said atoms of hydrogen, not molecules of water. Atoms of hydrogen in water. So let me give you a real simple metaphor. If we have 10 wheels, how many bicycles can I make? 5, because it takes 2 wheels per bicycle. So the ratio of wheels to bicycles is what? 2 to 1. 2 wheels per 1 bicycle. Everyone okay with that? All right, let's look at water now. H2O. If I have 10 molecules of water, 10 molecules of hydrogen, how many waters can I make with that? 5, because it's 2 to 1. 2 hydrogens per 1 water. Exactly the same concept. Okay, so this one's asking for hydrogen atoms. So we're starting with 345. And we need to get to moles like we did before and under STP because it's a gas. Now we're going to, now, up at the top one, notice I said 602 times 10 to the 23rd molecules. Because I want to know how many molecules of water. Here I want atoms of hydrogen. So if I know how many bicycles I have, then I can find out how many hydrogens I have. Okay? Because now the ratio is 2 to 1. So the first thing we're going to do is calculate total molecules. That doesn't give us atoms, though. So we need a conversion factor to go from H atoms to water. So it's a 2 to 1 ratio. Now molecules cancel, leaves us with atoms of hydrogen, which is basically 927 times 2. Since the numbers are the same. Now, what about the 2-to-1 ratio? How many sig figs is that? The 1 or infinite? Can we have in water 2.1 hydrogens? No, it's exactly 2-to-1. So it's infinite sig figs. So that's why the answer has 3 sig figs in it. The 2-to-1 does not count in terms of calculating the sig figs of the answer. Now I've got many works. Are there any questions about these two problems, these last ones? Okay, so some of you may ask, well, how can we practice that? We go to Canvas, Files, tomorrow we're going to talk about chemical equation balancing. All these gram mole calculations worksheet, that's a worksheet. Gas liter moles, STP worksheet. Grams mole particle worksheet. And mole conversion worksheets. Lots of practice in this. So if you feel like you need more practice, I've got tons of it for you. Okay. That's all I really wanted to cover today. Yeah. I need to count out the lectures. It's going to be after break though. Not tomorrow. Not tomorrow. Sydney was concerned. She looked at, she looked at the practice test. Because we've got to cover single and double replacement reactions, balancing chemical equations. Yeah. So there's more to it. Okay.